from the industry, right? So you are not in the industry yet, most of all of the listeners, the audience. So it will be divided into two parts: green trends in the world of organic coatings. I have always been a part of organic coatings. I'm not really an expert in the field of ceramics. So it's just organic coatings, and introduction to the soft powers that industry demands from all of us. Right. So about me, there is already I have been introduced. So this is a brief timeline of my journey. So as an intern, I started in Kansai Nerolac in Mumbai. I worked, it's a very lovely project that I have been so lucky to be a part of, is that of Tata Nano. So I was a part of the Tata Nano project, the protective and the top coat of the nano cars. So yes, I was under the guidance of Mr. Iyer, and I'm fortunate enough to work for them. Then I moved to Berger Paints, Calcutta, as a quality control chemist. I was looking after the finished goods, the raw materials, and trying to find the root causes of the process upsets in plant. Then I moved to, my God, I moved a lot. International Research Center in AkzoNobel, Bangalore. As a junior research specialist, I was looking after system recommendation for different OEM manufacturers, different automotive manufacturers like Nissan, Toyota, General Motors, Volvo. And I was recommending system for various, for various countries, for various legislations. Say the same Volvo is in California, is in Troy, or it's in Thailand or in India. So it's the same manufacturer, but different kinds of systems driven by legislation. I will come to that later on. It's not really complicated. Then I moved to Asian Paints as an R&D executive in 2012. I was mainly into protective coatings, but I was also doing some regional projects about anti-graffiti, experiments, and sort of a few innovation projects, which are not really commercially driven, but more of an R&D interest to the organization. But yes, I was mainly developing protective coatings for drinking water potable tanks, which are basically mild steel, so to protect them from corrosion at high temperature. So yes, in 2015, I moved to the UK as a product development chemist, and my industry now is glass ranging from decorative glass to huge jumbo glass, glass claddings, laminations, and also the fenestration industry. Fenestration industry can include metals, glass reinforced plastics, fibers reinforced plastics, PVC, ABS. So different kinds of plastics and their protection and their longevity. And then 2018, I'm still with the same organization, and now I'm having a small team, leading a few disciplines like quality control, technical surveys, and of course the R&D. So that's my timeline. Now I'll move quickly onto the green projects that I have worked on. Obviously, I have worked on quite a bit in the last 11 years, but I have only focused on the green trends, and which I've thoroughly enjoyed, because that is the way to go forward for all you scientists, budding scientists, or researchers. So yes, I thought this will be the most relevant part to have an idea that everyone is moving towards chemically, at least, towards a better future, better environment. So now this was my first one when I was in AkzoNobel. So chromate-free protection of aluminium body of an aeroplane. So previously, when I was, it's in 2011. So it was not yet commercialized back at the time, but researches was going on in different organizations like AkzoNobel, in Sherwin-Williams, in PPG in the US. So a pool of scientists were working on to remove chromate, hexavalent chromium. Okay, so as you know, I have been long detached from the basic chemistry, so you will know more than me and correct me if I'm wrong. The chromate is toxic, so it's highly toxic, but it is so efficient in in arresting oxidation of aluminium. It's a very simple mechanism. It is basically acting as a sacrificial anode. So it oxidizes itself first, protecting your main substrate to be oxidized and get degraded. So aluminium was traditionally protected by chromates, like metals like mild steel was protected by lead. So lead is a heavy metal, chromium is a heavy metal. So the replacements were necessary, especially in the field of aviation, where it's a constant threat. It moves one airplane. Imagine one airplane just doesn't move from Delhi to Mumbai. So it is only under one legislation. It can be international. And that should comply to the changing legislation of the visiting or the host country. So that was the need of the hour. So I won't go into the details, but so the replacement of chromium is what? So we worked on different technologies, like sol gel technologies with titanates, titanium chelates. We worked on molybdates, vanadates, phosphates. Um, it's basically the same. There are two ways of protecting any metal. One is sacrificial anode, so it will oxidize itself first, thereby protecting the substrate. So it has a lifespan. So when all the anodes are extinguished, then the body becomes susceptible. And now that is the time, be it for ships, be it for airplanes, be it for bridges, for tanks, everything. When all the anodes are gone, you see little dots of rust, on the body of the substrate, on the body of the metal. And then is the time to reprotect it. So you take the coatings off, all the protective layers off, and then recoat it. Okay. So reblanket it. So that is one way of doing sacrificial anode. Another way of doing is barrier properties. So you build like a blanket, one layer on top of each other, say an organic layer, an impermeable layer, a very hydrophobic layer. You stop water from penetrating to the substrate, oxygen from penetrating to the substrate. So you break the circuit and you get antioxidation properties. But in aeroplane, you cannot really put a 500 micron coatings on top of it because, weight is crucial. And the erosion, the heat, the cycle of temperature when it is up there in stratosphere and coming down back to ground, it's immense. So any barrier protection of high thickness will not work. It will crack. So imagine if something is of, you build something, it is easier to crack, but if it's thin, it is more flexible. So it was more of an anodic sacrificial method than a barrier property. So yes, the solution in a nutshell was phosphates, molybdates, vanadates, and titanates. These are the next generation metals for protection. This is really the bulk of my part. Yeah, I'm of my career, replacing isocyanates with carbodiamides. Now, if you look at all of us travel in cars, in trains, in any automobiles, we sit on bus seats, taxi seats, which are plastics. Everyone wears helmets. One chemistry is universal in the world of organic coatings, that is polyurethane. It is very durable, whether you are, in the gym wearing a nice trainer. So that foam, is coated with it is a polyurethane foam. It can be it can be coatings, it can be anything. But in the world of coatings, polyurethane is like a father figure, like sitting on top. It is so widely, flexible or diverse that in its application. So everywhere you go, depending on any application, isocyanates is the catalyst to have a polyurethane. Now, it's a part A and B reaction. Imagine a glue. You have two parts of a glue, you mix them, and the glue, it hardens and you get the adhesion. Similarly, it's a reaction between two parts, A and B. Part A is, it can be anything. It can be a polymer with, an acrylic derivative, an acrylic polymer with hydroxyl, secondary hydroxyl group. It can be polyester polyol, okay, derived from a polyester. with the secondary hydroxyl group. Now, this hydroxyl will react with isocyanates, which is NCO. All right. So I'm not going into the details. Okay, you know, back when we were at your age, at least in my family, I didn't have the liberty of Google and internet. So there is no point, you know, bombarding your head at this time with all the reaction chemistry. Just know that isocyanate is a part of the two-part reaction. So now isocyanate is harmful in the sense it has got reproductive toxicity. So the whole world is moving. It's still in now. I'm not saying it's a trend. This one is a trend. Chromate free now has, you know, it's most of the companies, it's commercialized. You have alternates to chromates. Not many alternates to isocyanates yet. We are still using this chemistry, but we are struggling, and we are struggling hard, and hopefully we'll come up with a solution. So I have been fortunate enough to work with, at least in water-based systems, with carbodiamides. Now, instead of reacting, now if I have a resin, I have a part A with hydroxyl OH. Now, if I have a double OH, like a carboxylic, and then I react it with a carbodiamide, I get a very good mechanical and chemical resistance. This is number one, which we have established in the lab. That is very good. Now, what is bad? Why then? If it is good, then why it is not implemented yet? That is the question. The question, the struggle is the kinetics. The hydroxyl and isocyanate reaction is very fast. Excuse me. It's very fast. So you mix them within 2 to 3 hours, it's dry. So whatever you have coated, be it a car or anything, it is ready to handle, it is ready to move to the next stage. But carbodiamides is a slow reacting. It's a thermodynamically stable product, but it is not kinetically. So it takes time, and it cannot be catalyzed readily. So it will take 24 hours. So imagine the present chemistry, traditional classical chemistry, which is so well accepted in the market, it's 2.5 hours, 3 hours. And carbodiamide is like 24 hours, or to achieve its full hardness, 48, 72 hours. So it's a good comparison will be, imagine 2020 and a test match. You know, everyone watches 2020 because it is commercially viable. You know, all the sponsors, you know, all the Dream 11 and everything, everyone watches because you get quick result. So even industry, time is of essence. I will come to that later on, why time is of essence. So if I can do 100 cars, or I'm giving you a number, say 100 things or 100 pieces of glass in a day, why will I slow it down to 50 or 20? So it is a huge cost impact. The green chemistry, you know, saving the world and all those things, okay, they are in the background. But in industry, you always have to understand, not everyone is an Elon Musk. So money and time and money, they are like energy and mass, you know, they convert. So it's immense. So it is not yet commercialized or not yet accepted. Now, why then it is a trend? Why it is a future? Because the governments will impose legislation, will impose restrictions. So what is like a luxury today becomes a necessity tomorrow. So all those business owners will think, okay, I cannot do 100, even my competition cannot do 100. So the fight becomes 20 versus 20. So no one loses out. So that is the way, you know, moving towards a green chemistry. But no one wants to be the first guinea pig, sacrifice the sacrificial lamb, and, you know, take a cost hit. So that is one thing. Moving on, this is a very niche, how do you call it? In terms of impact, or in terms of its extent is the right word. In terms of its extent, it's not big, but it is massive, especially related to my career. This has been one of the most challenging projects that I have ever worked on. Why? I'll tell you, because I am in the UK formulating for the region, you know, for UK and Europe. NMP is banned. NMP is, you can Google it, N-methylpyrrolidone. Okay, it has got a very complicated structure. Actually, I'm joking, it's not. So it's a solvent. What it does, it's needed. So when you are doing any emulsion polymerization, you need co-solvents, you need, your activating solvents. So NMP for polyurethane dispersion, it's like, it's the best friend of a polyurethane dispersion, because that polyurethane dispersion, when it is applied to, say, any substrate, whether it's glass, wood, metal, whatever, or even shoes, or even belts, or whatever, be it automotives, whatever it is designed for, that NMP is not just a co-solvent, but also gives a grip onto the substrate. So imagine, how engines lock to the, to the coaches of a train. There is a locking mechanism. So NMP helps as a locking mechanism of polyurethane dispersion to the substrates. Now, if I cut that NMP, because it is, again, reproductive toxic, then I'll be cutting the limbs of the polyurethane dispersion. So it becomes weak. Now, why the challenge? Because Europe has already phased out NMP, N-methylpyrrolidone. So the substitute was N-ethylpyrrolidone. So you increase the vapor pressure of your solvent, of your molecule, and you try to reduce its toxicity. But now, in the next 3 years, even N-ethylpyrrolidone will be banned. So the choice is actually zero. There is no choice. We have to move to environment-friendly glycols. Dow Chemicals, they're a big supplier of glycols, DMM, DPM, DPNB. So they've got all fancy, fascinating names. But why it is challenging, I'm coming to that, because when you'll be in the industry, if not related to this, you will face similar challenges. Suppose if you are in a global company where they have offices in, say, in the US, in Africa, in Asia, in Europe, in different, in Singapore, they will have products which are global. So one product should satisfy every region or every legislation. This NMP is not yet banned in US. Now, US and California, they're separate. The Californian legislation is stricter than the rest of the US. So we, as an organization, we have an office in Canada. So now we want to compete against the Canadian products. Now, all the Canadian companies, they don't have any kind of compulsion to get rid of NMP. So they are using their local raw materials, using NMP, making a low-cost product and highly functioning product. And here we are in the R&D of the UK, sitting here using European raw materials where NMP is banned, NMP is being phased out, but we have to compete. So keeping performance the same, we have to compete. That is the challenge. So we have been successful, but if you ask me, which one okay, I'll wait for a sec. Right. So yes, which one do I prefer? I prefer NMP as a chemist, as an industrial chemist. But which one I prefer as a student of science? I will say glycol. So this is one of the challenges, but it's a trend. Lowering VOCs by using coalescing solvents of high vapor pressure. This is very simple. It's self-explanatory. So anything with low boiling point will be evaporating very, very fast, and it will be released into the atmosphere. So you have to replace the solvents with high vapor pressure, which is of high molecular weight, and decrease your volatile organic component of your system. Now, your question will be like, am I not contradicting myself that it will take a long time to dry if it is high molecular weight? Because it is not evaporating. Of course, yes. But then the ancillary industry comes into play. Long wave drying systems, infrared drying systems, which will have a very good penetration to the backbone of the polymer, or to the bulk of the system, to the core of the system, and it will drag, because it's a long wave. Imagine a microwave, okay? So it will drag all the solvents out of the system. So now we are trying to meet the challenges of the production downtime by adding machineries, by adding different technologies. This is really important. Tin, as we all know, again, it's a heavy metal. So when we were learning chemistries. You know what? Let me take this opportunity to explain here why I have not gone deeply into technical and why I am more focusing into the soft powers. Because when I was at your age, learning about different chemistries, I thought, okay, an isocyanate reaction is initiated by a tin catalyst. It is dibutyl tin dilaurate. Okay, it's a heavy metal. It's a heavy long chain salt of tin. But so that is very, it is like granted, it is like taken, like, oh, this is a catalyst. But when I started working in the industry, some areas, like some legislations like the European, Californian, in Singapore even, tin is banned. So whatever I have learned in university is already not valid when I came to bench work. Imagine our mobile phones 5 years ago. I remember fancying a Motorola flip phone. When I have the money, I'll save money and I'll buy a Motorola flip phone. That was my ambition. But when I could really save to buy a decent phone, Motorola flip phone is like, it didn't even exist. It was gone. Now it has been relaunched a couple of years ago. But anyway, it is gone. That technology is gone. So whatever you're learning now might not be what you will be working next when you will be actually working. So it's invalid. It's for me, in a very rude way, it will be a waste of time. So yeah, so this is an example of how things changed from my academic to my industrial career. So now this DBTDL, dibutyltin dilaurate, has been replaced by DAPCO, diazobicyclooctane. So it is a metal-free catalyst. It is a different mechanism. It is a slower mechanism, but it is an acceptable mechanism. So people are slowly getting rid of tin. And it's successful. To be honest, it's not like the carbodiamides. It is successful and it's running commercially. So if you have any question regarding these five or anything, just shoot later when I'm done. And if you're interested, and I quickly move on to the evolution of legislation. Why these green trends? So the European legislation and the Californian legislation have always been strict. I remember working in AkzoNobel for Volvo. The same Volvo car is in California, is in the rest of the US, is in Asia. But so if you are Volvo, I give you a specification, you know what? Protect my metal from these things. And you make a formulation. But then you realize that part of my formulation is not allowed in California. It's not allowed in EU. So what? Volvo stops its business? No. So you will have different systems for different continents, for different legislation, yet fulfill the same performance. Okay. So that's what strict regulation does. Even revisions in legislations of US and many Asian countries. You'll be surprised to know even China, who is the one of the top two polluters of the world, are charging taxes, high charges for emission of solvent. So a country like China is also cutting its solvent use. So India is not far behind, all I can tell you. And also, this is another thing that people are getting more and more aware, more and more connected to the rest of the world. Like, no one uses this in Singapore. Why should I use it in Malaysia? Why should I use it in Mumbai? So customers are forcing it. So it's a reverse system, not always the government. Sometimes the end user also forces a change. So he will, or a company will say, no, I don't want your product because it has got tin in it. So you have no choice. You have to go for another, an organic catalyst. So that's how it is. Even the health awareness in terms of audits, in terms of certification of companies, which will give them, a prestige in the world of industry, always want to go for greener technologies. So now it is the soft superpowers. So yes, an essential nutrition. Now nutrition to what? What is nutrition? Nutrition is what you eat to give what? To give nourishment to your health. So here, as students now, your health is your knowledge. Chemistry, knowledge of chemistry, subject matter is your health. Your nutrition, which will nourish your health or your power, is the soft power. Communication, anywhere you go. All right. Now, Let me tell you why I am telling this. This is more important because not everyone will come to coatings, not everyone will go to optics, not everyone will go to, to pharmaceutical, but this becomes the backbone. I feel everyone should know it because in the first 3 and 4 years of my life, I learned it the hard way. I thought, I know everything. I am the Isaac Newton of this company. Why am I not growing up the ladder? Why people don't like me? I should be celebrated. I should be a celebrity. But no, it doesn't work like that in an industry. It's a team game. And communication is the icebreaker. And communication doesn't mean that just your relatives or your friends or your teachers, not like that. It can be anywhere. If I am in the UK, I have to learn about the politics of the UK. I have to learn about the talking about the weather. So that is an icebreaker. If you're in Italy or Spain, you have to learn to talk about the food. If you're in Russia, probably vodka. If you're in India, probably politics. So I don't know. But yes, communication, wherever you are, you need to communicate. You need to communicate with your team, and not just team within your level. You are not communicating with your fellow chemists, because once your formulation is done, it is going to production. So you have to communicate to the production head. You have to communicate to the workers, to the laborers who are actually producing your product. And then, you know what? You will come to know that there are so many things that you don't learn in books. Okay, those are the things that you collect out of experience. You will see you have never learned in a book the technique that a factory worker is using to do to make a process feasible. So it's a wonderful world. I made that mistake. So I think keep your ears, eyes open. There will be frustration, there will be many things, okay, you are too young, you don't know anything, but you know your subject matter. But if you know these things and be clever enough to utilize this to your benefit, it helps you immensely. Trust me. That goes on to my next point: curiosity and seeking street smartness. Now, curiosity means interactiveness. Curious, what is that? Why it is like that? So why it is not done in this way? So, and when you ask questions, no question is stupid, like I told you before. You will see that, it is done in this way. Okay, let me think of it in another way. So you can come with innovation. Now, what is street smartness? What is not street smartness is me. I'm not street smart. Okay. So I want you to be street smart. I thought, okay, if I have the knowledge of chemistry, if I have the knowledge of physics, yeah, I know everything. Doesn't matter. But street smartness is getting things done the right way at the right time. Getting out of trouble. So if you have a complaint, if you have a process upset, okay, you are fighting against time. You cannot use all your equations and all those reaction chemistry. You simply don't have the time. Time is of luxury here. So you have to be street smart to know how to give a first aid to the situation, how to put a band-aid to the situation. Who should I go to ask for a solution? So if you're an Isaac Newton or a Richard Feynman in one fine corner in the laboratory, you don't even know. You don't even know who to ask, who to go for. You don't have a solution. So it is a very ruthless place in industries. I don't know about other industry, in my industry, because I come from fast moving consumer goods, because it's a very high volume industry. Okay. So time is money. So you have to be street smart. Next, importance of time as a constant dimensional reference. Excuse me, this point is for my love of cosmology. I will digress a little bit. Quick one. Okay. 1-2 minutes. Dr. Tyson, Neil deGrasse Tyson, in one of his interviews said, we live in a 4-dimensional world, right? So I hope you understand. So 4th dimension is the time. So X, Y, Z axis, and you have time. So an example is, okay, we are doing it in a Zoom meeting here, all right? Everyone is in front of the screen and everyone is there. But imagine if I was invited to your campus. So you tell me, okay, Shubhajit, can you give us give us a seminar, like a speech on such and such topic, 3rd floor in the seminar hall. So I will ask you what time, isn't it? So what time should I be there? So you gave me the XYZ coordinates, but you didn't give me the time. Industry is driven by time. Time is money. Like I said, it's the energy and mass equation. So if you have a fantastic product, like world beating product, but it was not delivered in time, you are out of the race. So all you want is what customer wants, to deliver that, even if it is not perfect, just to meet the expectation of the internal stakeholders and the external stakeholders, deliver it on time. So a product with, with many flaws, but not as many that it won't succeed, but say a product, an non-perfect product on time is worth more than a perfect product past time. So it is of immense importance. Otherwise, your competition will come and grab the market. Now, this is especially important for R&D. There are already products which are running in the market, which is the bread and butter of your product, like Colgate, like television, Sony television, Colgate toothpaste. It's running. But if you want to do an innovation and other companies are trying to grab that market, then it is an open race. Try optimization of a process, reducing waste, right? So you make a fantastic product, but the process to make that product is very, very tedious, very hard, very long, very complicated. It is not a sustainable process. It has to be like either it will be you or a process chemist or a team which will have to optimize the production of the process. Now, what is a process? You have input, you have, you have a little bit of cooking, you have an output. So that is a process. So that process needs to have less and less and less standard deviation, less and less and less of waste. And then only it becomes sustainable, repeatable, reproducible over a period of time. If there are too many errors, it is not. Deliverables. Key performance indicators in industry, you are there for a reason. You are not the Superman saving everyone, okay? Wearing a cape and that dress. You have a function, you're a part to play. So imagine you have a set of targets and you think of, again, I'm going back, I have nothing against Newton or any other scientist, but it's just to give you an example of being a geek and a nerd and being an industry R&D. They're two very different things. Key performance indicators, you'll be judged on. What was your target at the beginning of the year? How many did you achieve? Again, within time. So you have to keep focus on your deliverables that, okay, I want to invent, I want to be, the next thing, but was that your target? No. So that is a secondary thing. First, finish your targets. Do not lose sight. Next, internal and external stakeholders. You work for your customers. They pay our salary. So, period. Whoever you are, customer is the only thing. Now, your internal customer will be the sales. The sales will come to you and tell you in R&D, you know what? Give me this product. I want this. So your customer is the sales. Sales customer is the external customers. So you have to understand who is the end user. How do I satisfy them? They might not need a very, a very SpaceX or a Tesla kind of a product. They don't need that. They don't need that innovation. Just give them a street smart product which fulfills their need within a reasonable cost. So you have to understand that. Sometimes I did that mistake. You know what? I will make this formulation more robust. It will be the best, but it's not needed. It's out of cost. So it's really useless. You might feel like a creative satisfaction, but in terms of commercial value, it's useless. Now, here it is. This is what you'll be doing. Chemistry, you use your knowledge of chemistry to product. Now, that arrow has the process in it. So chemistry, you use process, you make it in the form of a product, and that product goes out to customers. So this is your cycle of work. Whatever you do in an industry, document it. All he understands is documentation and figures. And that is the man responsible for your growth, for you to grow up the ladder. You are not in the industry, to win the Nobel Prize. If you win, you surely, maybe if you win, it's 1 out of a million chance. All you have to do is fulfill your ambition, grow up the ladder, have your own team, and evolve. Okay, so when you start your career, you feel like, oh, I will make a Superman product. But ambitions, change over a period of time. When I was 25, I used to feel like, oh, I'll make a polymer, which will give me 10,000 hours of salt spray resistance. But now I have other ambitions. I will have other ambitions when I'm 45. So ambitions over a period of years, it will change. So to fulfill those ambitions, whether it is personal or professional, you need to have figures to prove yourself. Oh, yes, I have done it, but it's not in my head. Makes no sense. You have to document it, you have to present it, and make that noticeable. Because if you document it, if you present it, it becomes noticeable and you are talked about, right? Now, understanding risk, legislation, safety, and feasibility. So the non-technical people of sales, of business, of market will come and tell you, I need this product, but you are the one who has knowledge of the risk, of the safety, of the legislation. Oh no, you cannot have this product because this is banned. Oh, you cannot have this product in this time because this is banned. Oh no, this product is not safe for our factory premises. We need to have these precautions. There is a risk to the workers. You need to have a periodic urine test if you are to follow this process or if you are to use this chemical. Feasibility, oh no, this is not feasible within 1 year. So it has to be 2 years. So be very careful when you agree to a project. When you are at that level and when you are in charge of a project, you have to understand the risk and legislation and safety to determine the feasibility of the process or the project. Leadership and decision making. This will come over a period of time. So if you look at the first point, communication, this is a child or a derivative of communication. So once you grow up the ladder, you don't have to analyze the reports coming out of or the results coming out of a differential scanning calorimetry. It's not needed. Maybe when you are 24, 25, you say, this is first order transition, this is second order transition. Okay, it's very good. But when you grow up, when you're a leader, all you need to know is to know who understands DSC, who understands process, who understands root cause analysis, who can do this. So then you are a leader. Yes, you have the subject knowledge. Yes, you have the overall depth, but you need to know, like Saurav Ganguly, he knew when to send Dhoni to number 3, when to do this, when to do that. But was he the best batsman? No. Was he the best bowler? No. Was he the best fielder? No. But he knew who the best fielder, who the best batsman, who the best bowler was. That's why he's a leader. So that's why decision making comes into play. Some people say leadership is born. Yes, it is born, but you also can acquire it by communication and curiosity. So that is what street smartness is. Last but not the least, which I have learned, is personality. You cannot be, the mad scientist of Back to the Future, looking like Einstein with frizzy hair, running about in the factory. No, it is good for academic, but in the industry, you can be like that, but trust me, you will never grow up the ladder. So personality, walk fast, walk straight, look clean, smell good. This is important. Show intent. When you respect yourself, when you look good, people will follow you. It's the last point, but it is very, very important, right? So I end it here, and I welcome all your questions. Thank you. Anyone? Question related to anything, including my hobbies. So go ahead. If you still have the time, I am not sure. I'm not timekeeping.
The session is open for question answer now. So all are welcome to ask questions if you have.
Yeah, I'll be very happy if you all use my time. So go on. Don't feel shy. You can see there are some chats. Okay, thank you very much. Thank you all. Okay, thank you. But I will appreciate some questions. Like, you are my customers today, so use me.
So still our students are ready with questions. Thank you so much, Mr. Subhajit Chatterjee. It was really fascinating and engrossing session, I must say. And I'm very sure that your career journey is truly inspiring to the students who will be the budding scientist or who will be the academicians in the future. As you have, and especially I liked your last slide, that is the soft superpowers you mentioned. So so it's very important, and the way you presented it was very interesting. And as you mentioned, like it just not enough to be smart, but you need to be street smart. So that's I think mantra the students should take it.
Yes, I
You know, very.
So I made that mistake myself. So I got a head start after. I'm not a head start. I learned it after 3 and 4 years. After wasting 3 and 4 years. So if they learn it from now, they will save that time. So so it helps them.
Exactly.
Indrani, I have a question. Indrani, can you hear me?
Exactly. And yes, sir, please.
Yes.
Yes, Dr. Ghosh. Ghoshar is with us, and he's having a question.
Yes, Subhajit, this is a very nice lecture. I think it will be very good for, brilliant thing for students or faculty members who want to get a startup project or something like that. And how to finish the startup projects, as you mentioned, the soft power and all this. It's a very nice lecture. Now, I have a question that you're talking about aluminum something, replacing chromate or something, right?
Yeah.
Chromate-free protection
very fast, yeah. So, have you tried anything of nanomaterials here? For these days, paints, they use nanomaterial, particularly some form of alumina or something.
Yes. There is a Dr. Ghosh. It's well, sometimes it's the mindset. Like when I was in Bahrain, I'm not demeaning anyone here, and I will not name my manager. I was working on protecting mild steel, normal mild steel from corrosion, saltwater, seawater resistance. And I worked on polyaniline. Okay, so I got with 5 micron of film thickness, I achieved 2,500 hours of salt spray, which an epoxy or a zinc-rich system, a sacrificial system, and a sacrificial and a barrier dual system or hybrid system will give, say, 1,500 with a 300 micron thickness. So when I went up to him with the presentation saying, "Look, I have done this," so his first answer was, "Is the present system not working?" I said, "Yes, it's working. The present system is working, but no one has done this, or this is not commercialized yet." And he said, "Very good," but he never took interest. So it's a kind of market perception. There is a perception is handling nanomaterials or those nano dispersions over a period of time as a raw material is, in terms of storage, is critical because it is highly susceptible to temperature, and in industry, storage life or shelf life is very important. So I have fast moving product, I have a slow moving product. The customer might buy this product today, might do the application 6 months later. Now 6 months later, the being of such high surface area and such a delicate nano dispersion, that product might settle, it might coagulate. So the usable time, if the usable time of my product is right now, then yes, I can use nanomaterial, it can be done. Of course, it is costly, sometimes it's not commercially viable, but the two hindrances, like you were saying, I would love to use the nanotechnology. There is so much of work going on in nanotechnology, but the two hindrances, one, lack of inspiration.
Yeah, what I'm asking is it possible to have something like heat resistance nanomaterials? If you use nanomaterials, there could be heat resistance, So that is one possibility.
It is possible, but what I'm not a manufacturer of nano dispersions, but what I feel is, Dr. Ghosh, is the lifespan of that raw material in a factory or in a real life might not suit that product. Like, okay, every 6 months I might have to replenish because it's such a delicate product. So sometimes from commercial viewpoint, of course, the performance viewpoint is fantastic. That's the future. But maybe from commercial viewpoint, compared to my normal micro dispersions, nano dispersions are more.
And it's also very important to have, uniform size. Otherwise, nanomaterials doesn't work very well. That's one point.
And also,
India cannot, synthesize simply alumina nanopowder of uniform size. Various paint industries, they have to buy it from, from other countries
True, but
for their industry.
I think there is a lot of nanotechnology work going on, and there's a pioneer. I forgot. Even his second name is Ghosh. I think he's in my LinkedIn connection.
Bargott Paints also, they purchase nano alumina from France or somewhere.
Yeah, yeah. No, nanomaterial with its surface area, it entirely changes the performance. Here, it says, what do you think about hard work and smart work? Everyone mentions about the importance of smart work in order to be successful. So what exactly is it? Okay, Rosie Banerjee. I would say hard work within time is smart work. Okay, so smart work, when you say smart, immediately the first thing that rings in your ears is time. Hard work might, you are toiling. But smart work means quick fix or a smart fix, not a quick fix, a long fix, but a smart fix. So it is hard work. You have to work hard. There is no substitute of hard work. Trust me, all these soft superpowers and everything, which I forgot to mention, thank you for reminding me, it's hard work, okay? Hard work within time is smart work for me.
So any other questions from audience?
Okay, you have my email ID. If you have any
Okay.
question, you can shoot.
Okay, so if you have any questions, you can, okay, I have, I think, okay, there is one more question. I think growth mindset is another one to grow in career. So what is your view,
First of all, my
Mr.
smile
Chatterjee?
is for Shobit. He's my classmate. Partho is here. Shanti is my
Okay.
classmate. Orphan
Okay.
used to be, Orphan used to be in my football team. So yes,
Yes, I came to know today that Arpan is a very good football player from you.
being
Thank you so
with,
much for that
yes, he's
information.
training.
We didn't know it.
I think
Being with him.
growth mindset is another one. Yes, yeah.
With where did you get your BSc degree?
From Scottish Church.
Scottish Church.
Yes.
So you're a student of Rana.
Yes, I am still in touch with Dr. Sen. I have a special relation with him.
Rana is my student.
Oh, okay. Okay.
And Rana's daughter is also my student.
Okay. So it's really nice. It's a pleasure to know you. Yeah, I'm still in touch with Dr. Sen. Yes.
Yes.
Yes, Tobik, it's nice to hear from you. Yes, the ambition is important. It's if you're in the industry, you have to think big. That's right.
So with this, thank you so much again, Mr. Shubhajit Chatterjee. We will love to listen from you again in some our future endeavors. So thank you so much. So with this, we will move to we are really running out of time. So we will move to our next speaker. With us today, we have our next speaker, Dr. Saurabh Kapoor. Let me take this opportunity to introduce Mr. Kapoor. Dr. Saurabh Kapoor is currently working as a research scientist in the domain of optical fibers in Starlight Technologies Limited, which is located in Aurangabad, Maharashtra. He has received his BSc in Physics in 2009 and MSc in Physics in 2011 from the Department of Physics of JNDU. He obtained his PhD in Material Science and Engineering from the University of Aveiro, Portugal in 2014. At present, he works as research scientist in the domain of optical fibers. And prior to joining Starlight Technologies, where he is in, he has worked as postdoctoral researchers at Aalborg University in Denmark and Rutgers, which is a state university of New Jersey in USA. Dr. Kapoor is author and has been co-authors of 23 research articles in the field of glass science. He is a member of TC04 and TC20, which is the biomedical classes and optical classes respectively in the technical committee of International Commission on Glass. So thank you so much again, Dr. Saurabh Kapoor, for joining us. We will, without much delay, we will like to directly move to Dr. Kapoor for his talk. Over to you, Dr. Kapoor.
Thank you for the introduction. Hi, good afternoon, everybody. So, is my screen visible?
Absolutely.
You can see the full
Yes,
screen,
yes.
right?
Exactly. Yes. Thank you.
Okay, okay. The title of my talk today is Looking Through Glass, Science, Technology, and Beyond. So, the talk today, I'll be keep it very general for just an overview. What are different applications of glasses and how we implement the basic knowledge of glass science in day-to-day problem solving in within the industry and for new product development or process improvement. So so I'll start with next. Yeah. So just like you gave some brief introduction. So I'm working as a head of glass research division at Sterlite, and my PhD was in glass and glass ceramics for bone regeneration application with Professor Jose Maria in University of Aveiro. And my research interests at the moment are composition, structure, property relationships in glasses, chemical durability of glasses, or you can say glass-water interaction, and mechanical properties of glasses and optical fibers. So in these times, we can say easily that we are welcome to the glass age, because initially there was Stone Age, Bronze Age, Iron Age, but at this moment, as we see, moving from 3500 BC to today, there have been enormous change and enormous increase in the application of glasses. If today we are talking to each other, it's just because of the optical fiber. In all this pandemic, all these virtual classes, all this virtual world have been created due to internet, which is all due to the presence of optical fiber. If we see now, if this is one of the internet live stats, if we can see how much amount of internet users are increasing day by day. And this is all with relation to the optical fiber. This amount of data traffic is being generated just now. So glass has a very important role to play at this juncture, and definitely the applications are increasing from cover glass screens to the structural glass. So it's one of the most important materials if we see from last few years. So what is glass basically? We've always read about it, we see it around, but what is glass? So glass, the word comes from glacium, or the Latin word vitrium. We also call it sometimes vitreous. So the classical definition of glass was it is a supercooled liquid. But how true it is, with changing time, it has evolved, because if it is a liquid, all are the medieval windows which are present, which were seen in Europe, they were thought to be flowing based on these notions. So what we see that these windows, when they were repaired or they were taken out, they were thick at the bottom. So people thought the glass flows, but Professor Edgar Zanotto estimated the period in which the glass might flow down at the ambient temperature. It exceeds the limits of human history. So if it's not a supercooled liquid, and if it doesn't flow, so what it is? So why these cathedral windows were thicker at the bottom? So the answer to that is, in older times there was no proper manufacturing process to form uniform thickness glass plates or glass sheets. So what the glass manufacturer did, the glass blower created glass cylinder and then flattened them. And because of some reason, they put the thicker side of the pane at the bottom to give it a melted look. But this doesn't mean glass is a liquid, true liquid. So what it is a supercooled liquid or it's a solid. When we try to classify glass as a solid, one doubt which comes is to define in terms of three states of matter, which are thermodynamically stable. Glass comes in a thermodynamically metastable state. So whenever we change slight parameters, the properties of the glass changes. It attains a lower energy state. So we cannot classify glass as a solid. So if it's neither a solid or nor a liquid, how do we define it? We define it as an amorphous solid. So a state between two states of matter. So glass is actually neither a supercooled liquid nor a solid. We classify it amorphous solid. So what is that? So in amorphous solid, what we see is what is different from crystalline is the random structure. If we see the crystalline, this is an image of crystalline silica. If we see the bond order or the constituent of solids are arranged in a regular pattern, three-dimensional structure, producing a crystalline solid. But in terms of amorphous solid, we don't see a regular pattern. So a randomness is introduced because of variation of bond angles and bond lengths, which forms an amorphous solid. But here we see that are all amorphous solids as glass? No, that's not there. We don't rate all amorphous solids as glass. What differentiates any amorphous solid material from a glass is the concept of glass transition. So I'll just go through small basics of glass transition. Here we see a volume temperature curve for a crystal. So when a small amount of liquid well above the melting temperature, when we cool it down slowly and enough time is given so that crystal could grow, if there are sufficient large number of crystal present, it grows and the enthalpy abruptly decreases, it forms a crystal. So the volume and enthalpy both decreases abruptly. But in case of glasses, if we avoid the crystallization to occur, if we cool that same liquid very fast so that it enters a supercooled liquid region, what happens is, as we cool down, the viscosity of the glass slowly increases, and the viscosity eventually becomes so great that the atoms within the glass are no longer able to rearrange to their equilibrium liquid structure during the time allowed in the experiment. So the structure appears to be frozen in the laboratory time scale. So when we see that, so the enthalpy goes down, and at a certain point, the enthalpy or the volume begins to deviate from the original supercooled liquid line, because the rate of change of volume, what we see with temperature, changes, because in this region, what we see, the viscosity increases significantly. Thus, we see that in this region, when we deviate, this region is, when the deviation starts, this region is called as the glass transition temperature, where the viscosity is around 10⁻12 poise. But in the solid region, we have the viscosity of around 10⁻16 poise. So what we call the smooth curve between the onset of departure from the supercooled region and the completion to a seemingly rigid condition is termed as the glass transition region or the glass transformation region. So this is very important characteristic for a glass in any industry, let it be optical fiber industry or any industry related to cover glass screens. This is a very important property which is used for many of the process parameters. So moving on to applications of glasses, what we see that glasses have been used in numerous applications. One of the application is healthcare. If we see that one of the initial microscopes which were developed and which are currently helping us in the pandemic to find out the vaccines and everything, microscopes had a glass microsphere which was used as a lens. Other examples which are commonly used are thermometers and lab wares. Other than that, one of the most recent materials which have been developed from glasses are bioactive glasses, which we can see the Sensodyne paste which we use at our homes daily as a glass particles in it. If we see the carton and see the ingredients in it, it says phosphosilicate glass. So this glass was discovered by Professor Larry Hench in 1970s, and up till now it has been used in millions of people in even as some implants. So how these glasses work actually? What happens is these bioactive materials, they form stable bond with the tissue through surface reactive layers. So the chemical nature of this bond enhances the interfacial adhesion of the implant. So nowadays what is happening, earlier the implants used to be metallic implants with no ceramic coatings or anything. It's particularly in case of knee replacement. What people are now having, they're having ceramic coated implants which promote the adhesion with the tissues around it. So the rejection rate or the life of the implant has increased considerably because of the nature of the coatings, which are generally bioactive in nature. Also, so if we see here, this is one of our experiment where we did in vivo tests. So what we did was, in this, it's a goat. So the bone part was replaced by glass, and these were evaluated after few weeks to see what is happening. So what happens is, when these bioglass spheres are implanted into the body, these react with the body liquids. So the silicon layer forms silanols and react with calcium as phosphorus to form calcium phosphate layers, which forms as a precursor to the bone part, which is a hydroxyapatite. There are several applications to these bioactive glasses. It has been used as bone graft in orthopedics and craniofacial. Some of them are also used as cochlear implants in the ear. And recent advances in the bio-tissue engineering, people are also trying to make porous scaffolds so that it can help the bone regeneration or bone repair by forming bonding with the body and also enhancing the cellular ingrowth. So how do we design these glasses? So as a students of chemistry, we have I was having background in physics. But when I started doing work on this, there was a lot of chemistry involved, particularly the inorganic part of it. So what we see when we design glasses, the glass structure impacts the properties of glasses. So what you want is, you want a stable glass which should dissolve in the body within a particular limit of time. You don't want the glass to remain in the body for longer period of time, and you also don't want the glass to dissolve immediately. So the bone regeneration or bone remodeling should be in sync with the dissolution rate of the glass. So what we do is, so that when the composition is designed in such a way that the silicate network predominantly forms a Q2 structure, where we have two covalent bonds forming in the glass structure, and the phosphorus which is there, it should have a structure where it is not connected to any other of the other phosphorus structures. So it should be in, we call it Q0, with no bondings anywhere. What happens is, with this open structure, when it's added in water, what happens, the dissolution rate is seemingly high, where phosphorus is released is very fast and in sync with other ions. So what we do is, we design these glasses, and then these glasses are tested for their chemical degradation. If we see here, these are the ICP results of those glasses, we see calcium is being released at the highest rate with change in zinc ratio. So when calcium, that is why I said the calcium is released with phosphorus forms the calcium phosphate layer, which is there. This is also a weight loss degradation study, where we see with increasing zinc, we are having a lower weight loss. So if we want to tune a composition, a silicate glass composition, we can add dopants depending upon their chemical properties. What are their chemical properties in terms of biological efficacy and also the chemistry? For example, a sodium ion which has a higher mobility will have a faster dissolution rate in glass in comparison to zinc or a calcium which has a lower mobility in comparison to sodium. So after 7 days of immersion, we do these tests in simulated body fluids. We see that these layer of hydroxyapatite, which is seen here, gives the XRD signature in this way, and after immersion we get these crystals formed on the surface of the glass, which are then emulated in the bodies also. So it's a in vitro test where we test the glass in the body fluids, and the properties which we see in vitro are thought to be better or thought to be benchmark for testing the glasses further for in vivo. So further moving glasses in technology, these days glasses have been used in several applications, particularly telecommunications and cover glass screen, our mobile screens. So here I will be properly discussing only optical fibers. So what is an optical fiber? So an optical fiber is a flexible, transparent material made up of glass. The thickness what we have in the industry in the present is 125 micron. It's slightly thicker than a human hair. It functions as a waveguide to transmit light from one side to the other. It works on the principle of total internal reflection, where we have a core, a cladding. So the core is a glass piece and the cladding is also a glass material. The coatings are polymer. So the functionality is such that the core is the main light transmitting area where the light travels. The cladding part is primarily protecting the core part and also to some extent protecting the signal loss in case of optical fiber on bending. And the last part is the coating. The coating primarily is used to protect the glass from any degradation with time, but particularly from water, because these optical fibers are very susceptible to water fatigue with long usage of time. So before moving on, we'll just do some basics of it. So what the single most important criteria for designing an optical fiber or for the application part is attenuation. So what is attenuation? It is basically a loss of optical power as the light travels along the fiber. So in optical fiber industry, the most important factor to design a new product is the attenuation. We need to, if we are improving the other parameters, we cannot afford to lower the attenuation part, particularly for telecommunication cases. So here the attenuation is dependent upon the elastic scattering from density fluctuations, concentration fluctuations, which form the bulk of the attenuation in the glasses. And other forms, unavoidable forms, are acoustic Brillouin scattering from acoustic phonons, Raman scattering from optic phonons, and other multiphonon edge. But at the as a glass research division, we are looking into the effect of different compositions and how to minimize the density fluctuation part. So as we discussed, the scattering losses are primarily due to frozen in density fluctuation, which are further added on by concentration fluctuations. What we see that during the manufacturing, when we are cooling the glass, as we have seen in the graph, when we are cooling the glass, uneven cooling or different rate of cooling will result in small pockets of high density and low density. As we can see in this figure, you can see some low density, some high density regions. So these density fluctuations interact with the light and result in scattering of light. Second part is the concentration fluctuation or the impurities. We don't want any impurities in the optical fiber, even a small amount of impurity. Just to give you an example, a ppb level of OH in the core glass will lead to rejection of the product by the quality team. So we don't want any kind of impurities in the optical fiber glasses which are there. So how do we reduce this? First is the density fluctuation. For density fluctuation, we use the concept of fictive temperature. Whenever we we are in meetings or when we are discussing how to improve the fiber, or if you will meet anybody from the fiber industry, he will definitely talk about the fictive temperature of glass, which comes from the fact that when we cool the glass slowly, the viscosity starts increasing, and at a point where all the molecules are frozen such that they cannot move. So so after that, the structure of glass cannot change. What we have is, we call it that temperature is fictive temperature. So on a volume temperature graph, it is the intersection of this extrapolated supercooled line and this cooling glass line, where we get the solid glass. So where they intersect, we call it as a fictive temperature. And the fictive temperature is highly affected by cooling rate. So when we are drawing the fiber, when we are creating the fiber, this is one of the critical parameters which we have to keep in mind while creating it, and even while designing a new composition for it, so that the fictive temperature of the glass is low as possible. So if we do it fast cooling, the fictive temp higher density fluctuation, so the attenuation will be higher. But if we do a slow cooling, the slow cooling case, the fictive temperature will be lower and will have a lower density fluctuation. But these comes at a cost. A faster cooling leads to a higher production, but a slower cooling leads to a lower production. A lower production is very expensive. So you have to keep in mind several parameters when deciding a process parameter for creating an optical fiber. So second is just an example to give it to you. So this is a glass with a higher fictive temperature. This is a glass with a lower fictive temperature. So if you see here, this glass is under a polariscope. So this glass under higher fictive temperature has a high amount of stresses, which are internal stresses, thus giving rise to density fluctuations. So the light interacts with different part in a different way. But in this case, it is completely transparent. So this glass with a lower fictive temperature has a complete removal of residual stresses, and this with a high amount of residual stress. So this we do anneal the fiber when we make it. So this annealing leads to lowering the fictive temperature of the glass. So, but why we only use silica glass? There are n amount of glass composition which can be designed, or n amount of materials which are present. Why are we using silica glass? The fundamental requirement for a material is transparent, and can be drawn into a fiber. Ice is transparent, but it melts at room temperature. Also, salt and sugar, but the chemical durability is very low. So how do we decide upon the material? So there are other transparent materials like glass and plastic. So why not plastics? Plastics, what happens is, the optical fibers for telecommunication purposes have to survive a large amount of weather fluctuations. They go from extreme cold to extreme hot. So the reliability part plays an important role in deciding the material. So what are the sources of silica? We also have a lot of sand which is available. Can I use sand in our making our optical fiber, or can I use silica available from our laboratory which is there? No, we have to use a material based on the requirements which are standards in optical fiber industry. What happens is, the quality of material which we use in making an optical fiber has a purity level up to 5 decimal places. We don't want any impurities. Based on types of impurities, we have categorized silica into different forms. One is type 1 silica, other is type 2, where the impurity levels are different. First is, in type 1, there is the OH level is less, but you have a high amount of metallic impurity. In type 2, you have high OH. In type 3, which we use in the optical fiber industry, it is very low on metallic impurities, but is high on OH. And Third is type 4. It is low on OH, low on metallic, but we use less amount of type 4 because it increases the cost of your production. So how do we make this type 3 silica? The basic process involved is the outside vapor deposition, which is also called flame hydrolysis, where the SiCl4 reacts with using hydrogen and O2, forming silica, and the HCl is sucked away using the suction mechanisms. So this is the highest purity silica which we get. So the problem with this is, since it has H2O2 flame, the silica soot or powder which is produced contains a lot of water. Here I can show you. So this is the deposited silica powder which we get from those machines. When we heat treat it, when we sinter it, we get a cylinder of glass which is then feeded into a draw tower. So the preform, it is melted in a furnace, and then it is drawn as a thin fiber, where in the process it has to be cooled down so that a coating can be applied and it can be UV cured simultaneously. Other coating is applied, and then it is packed for further testing. So we have been using GeO2. There are other dopant agents also which are available to increase the refractive index or to decrease the refractive index of the glass. So these dopants are chosen based on their influence on the glass properties and their solubility level, and how they are behaving within the glass. So the glass chemistry is very important in this case. For example, fluorine is used to lower the refractive index, but fluorine also tends to have other effects depending on, because of its mobility, it tends to crystallize. So you have to consider different properties when adding a dopant to it. So in terms of germania, the positive thing with germania is the germanium structure is very similar to silicon structure. So the solubility of germania with mild doping into silica is very good. So we use germania, and I think throughout the world, the majority of doping within the core glass is the GeO2, which is used in the optical fiber industry for telecommunications. So these are the major factors. Other thing which why don't we use other optical fibers? So people have been using other optical fibers made up of other compositions. For example, magnesium, calcium, magnesium silicates are used, calcium. But the problem with them is scale up of the product in industry is very important. Within the given structure which we have, we can design a new fiber, but is that fiber compatible with the already billions of kilometers of fiber laid down? So we cannot create another composition without considering the present structure and the infrastructure required to do that. So on those basis, the composition design is made in the fiber. Yeah. Thank you for your time.
Thank you, Dr.
Hello.
Kapoor.
Yeah.
Am I audible?
Just
Yes, you are audible.
Thank you, Dr. Kapoor. It was some problems.
Yeah, just a moment.
Okay, now it's fine.
Yes.
Thank you, Dr. Saurabh Kapoor. It was a very interesting and engrossing talk, and I'm sure students have got many information. Not only students, even for some of us, we got enlightened with the domain of optical fibers, where you discussed many aspects of optical fibers, starting from its processing to its application, and especially some of the challenges, like what are the materials can be used and what are some of the challenges with few materials. Thank you so much. Now this session is open for question answer. So I would like to address questions. Sir will like to address questions. So audience, students, you have any question, please. You can unmute yourself, you can ask, or you can write it here in the chat box. Do we have Ghosh sir with us? If sir is having any questions. Sir is there? Okay. Sir is there.
Sir, if you have any question, please ask, sir.
Yeah. It's a nice talk, Mr. Kapoor, Dr. Kapoor.
Thank you.
I want to know, ask you a question. How people prepare glass wools and why they're used so much in various cases.
So glass wools are basically, they are thin fibers. So what they do is, glass wools are, the composition is basically mineral. So you will get two kind of wools. One is glass wool, other is rock wool. Both are the same things, only the raw material is different. Glass wool is designed a designed composition, and rock wool is like they take a diopside mineral or some mineral and they melt it. So what they do is, the melt falls on a big roller. It's a big roller which is rolling down, and the glass falls on it, and thin fibers are thrown away in that roller after cooling down. So it immediately cools down as it forms a thin fiber. And that thin fiber, it's called a short fiber. What we talk about is a long fiber, and that these are short fibers, non-continuous fibers, we can say. So those are then, the wool is then packed down for the mainly this insulation application.
Yeah, thermal insulation, right?
Yeah, thermal insulation. Yeah. So in those cases also, the thermal properties, where we call the glass transition or the viscosity, that is really important, plays an important part.
So is it okay, if somebody uses glass wool on the walls and then paint it so for thermal insulation in the heat?
Yeah. I've been, when I was in Denmark, all the houses in Denmark are the same. They use a lot of glass wool. So they use a glass wool, then a gypsum or any other material to cover it.
Yeah, that's what I saw.
Yeah.
Then painting.
Yeah.
Okay.
I don't see many people in India using that. It's not very prevalent actually.
It's not cheap, I guess. It is somewhat costly, using glass wools for thermal insulation
I think so.
in a house.
Yeah, could be.
Yeah. Thank you for your talk. You can wait for other questions. Indrani, other questions.
So any students, because what I see is actually whenever we go for interviews, I have been part of few interviews in last one or 2 years. One of the things which we see as an interviewer when we go for a student is the I'm not like generalizing it, but most of them have I would say lack of homework. They know the predetermined questions are there. They know that part of it. But for example, I've recently interviewed few PhDs even, because some of the students will go for PhDs. What I would suggest them, that whenever they go for an interview, when I receive a CV, recently I have received few CVs, I have to search, even after sharing the job description, I have to search for the key skills which I need. So the CVs are not tuned in. They have, which I used to do the same thing when I was in masters, because we were also having less experience. You make one CV and you send this CV randomly to everyone. What happens is everybody has a different requirement to their own company or to their own specific job. So when the CVs are tuned accordingly and they are easily readable, they are more catchable. Because if what we see as a CV, okay, ठीक है, ये है, but when we need to search it, it is highly likely we might also miss those points.
Absolutely.
And the student might be having those qualities. It is very possible.
There are now organizations that are helping students and also many people to write CV, how to write CV, how to get you more publicity, so that you
Yes,
can write
yes.
a proper
Yeah.
CV. There are organizations now.
Yes, and also in
They are
our
helping.
in our university also there is one initiative taken from, there is career development cell which is called CDC. So they will be giving training for writing CV, presentation skills. So some of the expert that, but I mean they have been employed for that only. So we hope to have our students equipped with all of those things. But anyway, very nice. I mean, very useful suggestion, especially as you are in the interview board. Thank you so much for that.
Welcome.
So students, again, if you have any
Thank you.
questions, you can direct. This is a chance for interaction with sir. So please.
Any student, please. Any student from any institute, it's no problem.
Yes, of course.
Because it's a very renowned company, a very renowned industry. So I request you that you should interact with him. He is I have one question. So, Dr. Kapur, thank you very much for accepting our invitation, as well as giving a one. You have given a wonderful talk. Many of things actually I did not know earlier, especially this optical fiber thing. It is most of physics-oriented thing, since my background is from chemical science. So something is new to me actually also. But the reaction part and how to make the glass, how to tune the glass, all these things, that were okay with me, right? So my question is,
That was all mistake.
my thing is that it is not a technical question. Is that every year our student actually they some of our student actually they try to do some project outside the university, right? So in your company, is there any possibilities that we can send student, or is there any possibilities that we can have a collaboration with university that they can do some project here and deliverable thing, something they can learn some instruments?
Yeah, we do have collaborations and internships. We have lot of students coming from NIT, this Warangal.
Okay, okay.
And we do have students from IIT Delhi doing internships, and we also have fundings going into IIT Madras, where the collaborations are there. Yeah, definitely, it's a possibility.
So for that reason, in future, if we ask you, or if we contact you through Rupam sir or directly, so please
Yeah,
guide
you
us.
can contact me. Yeah.
Please guide us.
So the thing is, whenever next year, this year is
This year it's
completely
impossible. Last
now.
year also same thing it was there.
Yeah.
Hope this
So
situation will go very soon.
yeah. So I would say these are internships, and once we open an internship, I will definitely notify you pertaining to the job description, what we are looking at, and then we can have interviews or whatever it is required for the further process. So,
Okay.
so yeah, we are planning to have such kind of positions in future, because we do have a proper lab setup which is there at Sterlite, which with host of instruments, which students can have a joint project with academics to have an experience from industry, and simultaneously because we also have small academics projects within the domain of the interest what we have.
Okay.
So yeah.
Thank you very much.
Yeah, welcome.
So it's over to Indrani. Indrani? Indrani?
Yes, Arpan. So I
It's
think
over
with
to you
this,
now.
this session is, we are at the end of this session. So I request to take over Dr. Prantik Banerjee for the next session, right? We are over this session. This session is over. Okay. So thank you so much. Thank you all. I would like to request Dr. Prantik Banerjee to take over. Over to you, Prantik.
Thank you, Dr. Ghosh. Actually, this session is, jointly chaired by Dr. Arpan Manna and myself. And this session will mark the end of the 2-day symposium, and it is extremely difficult for both of us, Dr. Manna and myself, actually to summarize what we have been experiencing over the past 2 days. This, I would assume that this should have been, or rather this should be a good virtual stepping stone for the students of the university or students of other institutes who are attending this, as they will have a different horizon opening up before them. I mean, earlier the classrooms or the laboratories, and these days even worse, only the virtual classrooms, they tend to make their vision extremely limited, like those objects in the eyes of the horses, so they do not get distracted. That's for a different purpose, but unfortunately, the same phenomenon affects the students as well. But this particular symposium, with people, distinguished academicians, industry professionals from different aspects. I mean, they have enlightened us, they have enlightened the students, and perhaps all are getting benefited. Now, coming to the end of, coming to the end of the second session of today, that is to mark the beginning of this beginning of the third session. Sorry, we have three speakers with us for the last session: Dr. Shyamosri Bhattacharya, Dr. Rohan Gokhale, and Dr. Darren Tan. Dr. Bhattacharya will be the first speaker for this session. I'd like to ask Dr. Arpan Manna to give a brief introduction about her, and then we can move on to the lecture session. Dr. Manna, Arpan.
Actually, there is a problem, I think. So this time, this second session is end actually. The third session will start from 6:30 p.m. onwards.
Okay.
Actually, the time lag is there with US and India. So the 6:30 will be very early to them, but they are already they will give their lectures from 6:30 onwards. So I request all the participants to again come back for the third session at 6:30 p.m. Right? So for now, we are ending this session at 6:25. I request all of you again log in. And regarding the feedback from, so already Dr. Prantik Banerjee, he had written that if the session of this symposium is not finished, that how can we give you the feedback from? This is the main thing, because feedback from means your experience towards the symposium that we are conducting for 2 days. So at the end of the session, especially when the last speaker will basically delivering his talk, we will give you the feedback from. So you fill it and submit it by today or tomorrow, and automatically you will get the certificate upon submission of the feedback. So for this time being, I request you to leave this session, and I welcome all of you again at 6:30 p.m. today. Thank you very much.
So we'll meet again on 6:30. Thank you.